Yeah, I want to talk about a presentation today that I attended by Srabanti Chowdhury, professor at Stanford, and it's about material science, and it's also about how the world of silicon-based information processing is changing, and I think that's a lot more important, in my opinion, than people assign a tribute to, and that's partly because material science is just a bit of an obscure field. It's relatively difficult to understand. It's not as intuitive as other areas of computer science or of the compute stack in general. But it's really important because this is where it all starts, right? I mean, let's not forget that anything we do always starts with the actual silicon, with the metal. And whether that metal is classical or quantum, or whether it's silicon or gallium nitrate or diamond, that's maybe for outside viewers that might not be as important, but for the people who actually work with these things, that could be very, very crucial. And I think Srabanti's presentation was really interesting because she was talking about wide band gap materials, and gallium nitride is one of them. Diamond is an ultra wide band gap material. Now, I am not a material scientist. I'm not a condensed matter physicist. So take this with a grain of salt. What I'm trying to do here is really give a big picture explanation of something very intuitive without going into the technical details. And the concept is the following. If you had a material that allows for certain properties, such as, for example, extreme high voltage and also very high frequencies, you could improve power electronics in, let's say, devices like electric cars. And I'm going to focus on electric cars now because, of course, that's not very near dear to my heart as an investor in Tesla and as an investor in the transformation of the energy infrastructure from fossil fuels to electricity, from carbon-intensive fuels to electricity. Let's be precise about that. So silicon carbonate is one of them. Gallium nitride is one of them. Diamonds are ultra-wide bandgap materials. They all have something in common relative to conventional silicon, and that is high thermal conductivity, high breakdown electricity, and high electron mobility. So what this means is that you can have operating systems at much higher frequencies and a much higher voltage. So for example, when an inverter inverts or converts DC into AC electricity can happen at much, much faster rates. That increases power density, power efficiency, reduces the weight and makes things a lot more compact. For example, in power electronics, if you use ultra-wide bandgap materials, you could have a substation that is as big as a school bus today in as big as a suitcase. So that's what we're talking about here. Now imagine what this could do to a car if we start changing the proportions like this. And I think to me there's two important things. One is, of course, the scientific side of things and the question always, where's the science, where's the technology, and where's the actual entrepreneurship? And the other is more general. I think it's always good to think about, okay, what drives these innovations? When Tesla comes up with a new car like a Cybertruck, which does things that something at the size and weight is not supposed to be able to do, it's very often because of things like new materials and new applications in power electronics. For example, Tesla is using an 800 volt architecture for the Cybertruck, which, think about it this way, everything is at much, much higher energy potential. So things can happen faster, things can happen with more power, but in the same token, when you have this kind of, let's say, high octane architecture, you need materials that can withstand this, that can handle the heat, that can perform at these high frequencies and high temperatures and don't make mistakes. And that's where ultra-wide or wide bandgap and ultra-wide bandgap material come into play. So for new listeners, what we do here at the Not Even Wrong podcast is really try to give people a sense for what it feels like to run a hedge fund. We're in the business of investing in fundamentally new concepts and engineering practices, and material science is at the core of most of concepts and engineering practices. Not everything. Sometimes it's about new algorithms, sometimes it's about new types of devices, sometimes it's about new types of reorganizing data and training data, or even having the idea of using neural nets to train data. All these things can lead to innovations like we've seen in the Nobel Prize winning fact of Geoff Hinton, who introduced neural nets and became Nobel Prize winner in physics. So the same way, I think we have different innovations in different fields. And for us, it's always the same concept, which is how far away is the science from technology and how far away is technology from entrepreneurial application. This is the Not Even Wrong podcast. It's October 18, 2024. This is Krumdelko. For the day, the fund is up 25 basis points. The market's up 40 basis points. For the year, we are up 14.7%. The market's up 22.9%. We're underperforming by 8.2%. So this presentation, links in the show notes with the papers. The presentation is not in the show notes, but the papers that are relevant for this were co-authored by Professor Chowdhury. So it's about material science. It's about ultra wide bandgap materials and wide bandgap materials. So what is the bandgap? The bandgap is sort of the difference between when an atom ties the electrons to itself versus when the electrons are given free for conduction. That's the bandgap. And the higher that bandgap is, the more you can do with a material. If the bandgap is very narrow, your action space is very limited because, think about it this way. You do a little bit too much and the electron moves. You have to be very careful with the environment. You have to be careful with things like thermal management, power density, all that kind of stuff. The higher the bandgap, the more you can do. Now, the idea that I want to apply this to is really in electric cars. And one of the main applications, that's also what Professor Chowdhury was talking about, is the inverter. The inverter is the thing in the electric car that takes the battery DC electricity and transforms it into AC, which is important because the electric motor requires AC. That's what actually Nikola Tesla invented. And it has to do with rotation and magnetic fields and currents and things like that. This is not the place now to go into details. All I want to say is that if we have very high frequencies by which the DC power is converted into AC power, we can get more out of the same amount of energy. So we have more efficiency and more power density, which means we get more power per kilogram, for example, because we can get more out of that battery because it switches faster. Now that has to do with the technology of an inverter, which has active components and passive components, like a capacitor is a passive component. And the way you could think about this intuitively is that if I have a punching bag and I box, and I can box harder, then the punching bag will move faster. And if I box with high frequency, then the punching bag will be engaged a lot. And if I box with low frequency, the punching bag will not be engaged a lot. And the less the punching bag is engaged, the more power, the more energy is lost to nothing. The more it's engaged, the more it's being used for, let's say in this case, transferring electrical energy into kinetic energy, which is taking the electricity from the battery through the inverter to the electric motor and then have it run. So the fundamental idea behind this is really efficiency, right? There's a couple of other things in particular. Back to the inverter frequency, you have to imagine that if you have this higher frequency, you have higher efficiency and higher power density. You also, with wide bandgap materials, you have better thermal management properties. What that means is that wide gap, particularly ultra wide bandgap materials such as diamond, they conduct heat much better, and therefore you can have better heat absorption. Or in other words, also, they can handle much higher heat without making mistakes. A lot of times in semiconductor technology, heat can also lead to bit flips and all kinds of things. Onur Mutlu talks about this all the time. The more dense we are, the more heat we have, the more power dissipation we have, the more mistakes happen. So wide bandgap materials allow for much higher energy usage and heat with less mistakes. The higher voltage architecture, by the way, which has been introduced with the Cybertruck, is very important because that allows for a lot less cabling, a lot more compact design, less weight, and again, higher power density and higher energy efficiency with less mistakes. So fundamentally, what these wide bandgap materials allow is to have more juice out of the existing energy, or even bring more energy into the vehicle, use it at more efficiency, and have more compact design. And I think I wasn't able to talk to Professor Chowdhury, unfortunately, but I believe from reading her papers that the holy grail is this is not like a one-time Nobel Prize winning technology. I believe this is a tinkering problem where we have to go at it every iteration, every year. We have to get better at it. And I think that's what Tesla's doing. Actually, this would be an interesting question to the Tesla engineering team. Are you guys using wide bandgap materials? How important are they for inverters? How important are they for your electric motors? How does it change your magnet situation in the motor? Can you replace rare earth materials? Can you replace cobalt? Can you replace some of the materials by just having maybe different types of semiconductors that are used in the power electronics? I want to finish this episode with a more general comment for listeners. This is not the place where we typically talk too much about very technical details. It's not meant to be. Sometimes we do that, and it's a fine line we thread here because we don't want this to be a technical. This is not the limiting factor. We're not competing with the limiting factor or anything like that. Okay, kudos to them, by the way, for their work. That's not what we do here. We are really focusing on wealth creators, on hedge fund managers, on people like us that have knowledge, that are in the knowledge creation business, but aren't experts. We're not PhDs in material science, but we're supposed to make money with this stuff. And the difference between us and somebody like Professor Chowdhury is that it's our job to turn this into wealth. Her job is to make it work and hopefully also make money. I wish her and anybody else who is in this field to also make money. There's nothing wrong with it, but that's not their main job. It is our main job. And the way we make money is by identifying fundamental new concepts and engineering practices. So using these new materials allow for fundamentally new concepts, such as maybe much higher frequencies in inverter technology, much higher frequencies in power electronics in the car, faster, higher voltage, higher energy efficiency, lower heat dissipation requirements because it can work at much higher temperatures. So all these things combined lead to better performances. And if you can improve, let's say you take higher frequency of the inverter, higher frequency of the electric motor, less heat dissipation required, more compact design, and higher switching in other power electronics around the car. We have these 5 factors, and each one improves by 5% per year. Just by sheer math, we could have a double-digit, maybe 20% improvement every year in efficiency because each one is compound, right? It compounds, it improves not just itself, but helps the whole system get better. Maybe there could even be nonlinear effects that help the system improve. So let's not underestimate this. I think this presentation was crucial. That's also just as a tangent. That's why we're here. That's why we're doing these frequent visits to Stanford, taking advantage of the proximity of the place where we're stationed, but there's knowledge here that is very useful and sometimes gets actually translated into business because this is Stanford and that's what they do. But very often it's also knowledge that is almost like waiting there to be picked up. And I think this is one of those things. So we're going to definitely pursue this and also have a further communication with Tesla about this. Again, wide bandgap materials are a really crucial vector that could improve electric car technology massively over the next coming years. Thank you.